Thank you. Thank you for the invitation to this workshop. It's always a pleasure to come back to Vienna. And this, I think, is my fourth time, if I count well. So what I'm talking about today is based on some recent work with my student, Reza, who is still looking for a postdoc, and it's very good. I must say that I've been at NYU for more than 30 years, and this, I will say, in the top 3. It's based on these physical review letters, on earlier work with Reza and Uri Kohl, but it's actually mostly a review of things that we understood only recently, and our results have been published here. Okay. So here is a little rundown of what is going to be seen today. So I will review for, I don't know, maybe the 20th time in this workshop, the metric and symmetries of asymptotically flat space and the BMS algebra of asymptotic symmetries. I will describe in particular what one of the consequences of the symmetries called supertranslations and the ambiguity that they create in the definition of the angular momentum, boost charges, and their fluxes. And now, because of this ambiguity, I will motivate the desirability of new definitions of angular momentum and also the boost charges and also of supertranslation-invariant fluxes. Actually, there is an abundance of these definitions. There are several. I only described 2, so I will give a comparison of these definitions, different definitions of invariant angular momentum. And I will give a physical interpretation to the one that probably is the most appealing so far. Then I will discuss actually the thing that we really understood, our contribution, the problem with Lorentz covariance that exists in existing definitions of this invariant flux. And finally, once the problem is understood, it will be very easy to fix this problem and give a fully Lorentz covariant definition of the Lorentz charges and their fluxes. They have some ambiguities that do not show up at lowest order in an expansion in powers of the Newton constant. And I'll conclude with a final note of caution about all that we did, and I will caution about how uniquely defined is the entire construction. So let me start with this cartoon that says exactly what we want to do. So we are interested in asymptotically flat spacetime that has this Penrose diagram, right? And we'll be interested in particular in null waves, I mean, if you want, particles or waves with that propagate at the speed of light, so gravitational waves or electromagnetic waves or whatever, mostly gravitational waves. So we study a scattering process in which something comes in from past null infinity, interacts, and then scatters off to future null infinity. And I will look at what happens here. So I will look at what an observer at null future infinity sees. In particular, quantities that can be measured are charges. Charges defined at every value of the retarded time, and the difference between these charges at future null infinity minus the past is what we call the total flux. So that's the quantity that I will be studying. So I will be mostly looking at charges. And now the total conserved charge in the Bondi formalism, as you know, is the limit for retarded time going to minus infinity of the Bondi charge, so this object, and then fluxes that are the differences between Bondi charges and plus and minus infinity in retarded time. Okay, so this is the metric. We have seen it several times. The coordinates here are u for retarded time, r for the radial coordinate, theta for 2 angles of the celestial sphere. after the universal term that tells us that space is asymptotically flat, there are corrections, and in particular, the dynamics is really contained in the shear, CAB, which is a function of theta and retarded time. Other important quantities that appear here, as you know, are the Bondi mass aspect, also a function of the angles and retarded time, and the angular momentum aspect n, as before, which also depends on u and theta. And then the rest are quantities that are fixed in terms of the previous ones. Okay. Yes. Sorry, can you repeat the question clearly? Oh, yeah. For what I'm interested, so here I have assumed a certain fall-off conditions. Now, nothing changes for the leading corrections. Problems appear in the subleading ones. Since I'm interested in the angular momentum and not in superrotations, even if a failure of the peeling theorem doesn't change the results. If I were interested in superrotations, then yes, I will have to take care of that. Yeah, it's indeed. Of course, here you have three terms, right? And in particular, these two can be shuffled one into the other in many ways. So I'm using this notation because then when you look with this split of n and c, the angular momentum, the Bondi angular momentum is just the integral of n, but you could use other notations, of course. This metric is invariant under the transformations that we expect, Lorentz transformations. The Lorentz transformations act on the four coordinates. In particular, they act on the celestial sphere as conformal isometries. So they change the metric up to an overall scale, maybe. The scale could be 1 for rotations, right? And that's okay because we know that the conformal isometries, the global conformal isometries of the sphere are SL2C, that's the Lorentz group. And then there are supertranslations. That was the big surprise in the 1960s. At leading order in the radius, in the radial coordinate, they act on the retarded time by shifting the retarded time by an amount that depends on the angle. They also act on the shear in this way. Notice this f of theta depends only on theta, not on u. Right? So, but there is an infinity of translations because you can expand this f in spherical harmonics, and then you have all possible harmonics. And now, once you have given the symmetries, you can also give the charges defined in canonical way, canonical in the vernacular and in the exact sense. So in particular, the supertranslation charges are obtained by integrating the mass aspect with this an arbitrary function of the angles. Right? So you have many, many charges. Right? Now, some of them are more important than the other, and in particular, when you take a scalar here, f equals constant, and you integrate, you get the energy of your spacetime, and when you take a p wave, an L equal to 1 spherical harmonic, you get the three components of the total momentum of your spacetime. Now, we are interested mostly in angular momentum. The Bondi Lorentz charges for the angular momentum and also for the boost are given in this way. So you take, again, depending on notations. In these notations, you take just the angular momentum aspect and contract with one of the conformal killing vectors. So here you have the 6 generators of the Lorentz group. Right? And correspondingly 6 charges. These are Bondi charges. So as you know, Bondi charges are not conserved because if you have radiation, they decrease. Right? But so in particular, the total charge of spacetime, as I said before, is this object evaluated at u equals minus infinity. Since the y's are the 6 conformal killing vectors of the celestial sphere, they obey the conformal killing equation, which we'll use explicitly and implicitly later in various formulas. Now, if the total conserved angular momentum, as I said, is this object, if you want to look at the total angular momentum flux that is radiated when you have some radiation process that dies off in the far past and in the far future. This is just the difference between the Bondi charge at plus infinity minus the Bondi charge at minus infinity. Now, we should probably also compute this difference at finite u. Formulas become much more complicated, and this is work to be done. So far, what I will talk about today is about the total flux radiated in this space-time. Now, under supertranslations, the angular momentum aspect and therefore the Bondi charges at both plus and minus infinity change. So this n is not invariant, it changes in this way with the gradient of this f and the m, and j also changes. Notice that the change of j depends on, or n, right? So the change in angular momentum depends on a supertranslation and also on the mass aspect at the time at which you compute the charge. So if the mass aspect changes between plus and minus infinity because of radiation, then even the flux can be changed by a supertranslation. Now, one thing that we use all the time, and I'm reminding you of that, is the energy momentum, the fact that the energy momentum and the angular momentum fluxes can be written as a difference of two integrals on the celestial sphere, but they can also be written as integrals over null infinity, as a three-dimensional integral using Einstein's equations, in particular the equations that are really a constraint when you do null quantization. One is an equation that gives the retarded time derivative of the mass aspect as a function of the gravitational wave flux. Here I have no matter. If I had electrodynamics and or other null radiation, I would have to add something here. N is the Bondi news, which is the time derivative of the shear. So this is the equation, the UU component of Einstein's equations. This tells us that the mass aspect at minus infinity is an independent variable, but at any other time it's not, it's dependent by this. Right? And for the angular momentum aspect, it's the same story. Its time derivative is given by this nice expression over here. This expression depends also explicitly on the shear, not only on the Bondi news. And again, the UU and UA components are constraints in null quantization. Okay, so this is well known now. Well, we take the difference of the two charges, the difference at plus infinity and minus infinity, and we get that the change due to a supertranslation is non-zero whenever the mass aspect changes between plus and minus infinity, between the past and the future, due to gravitational radiation, as we have seen from the previous transparency. Yes? Mm-hmm. 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 Yes. So you want, well, I mean, there are two formulas for the angular momentum. Right? Thanks to this equation, you can convert, if you integrate in U, of course, this term over here will give you, and you multiply by a vector, you integrate over the sphere, right? You integrate and you get the difference of the angular momentum in the past and future. In this expression, instead, you have a three-dimensional integral that indeed reproduces the supertranslation with a little bit of work and using various properties, including the conformal Killing vector equations. So you multiply by y and integrate, right? So then you have to do some integration by parts. C transforms. C, in fact, it's important that it transforms. So the point, where was it? Yes, here. C transforms, and the angular momentum flux. So if you want, this is n is essentially, if you integrate on this sphere, it's the angular momentum. The derivative is the angular momentum flux. You can see that the angular momentum flux, unlike the energy flux, depends on the shear and not just on the Bondi news. So it transforms. And now, okay, this delta transforms. That's not crazy. I mean, there is nothing wrong with that. Angular momentum is not even invariant under translations. So it transforms under a translation generically. And the fact that doing a super translation can be thought as adding a gravitational wave in the limit that the wavelength goes to infinity shouldn't be too surprising. It is possible to change angular momentum by adding a very little momentum if you add it very far from the point where you measure angular momentum, right? I'm not calling it center of mass for a reason. So this P cross X can be big even if P is small. Well, I mean, good, that's true. There is nothing wrong or scandalous in that, but it may not be useful because in some instances, we want to be able to tell what is good and what is bad. We want to separate, for instance, the change in the angular momentum, radiation of angular momentum due to a scattering process or a black hole merger from some unobservable background. And when we see we have two black holes merging, there could be a very, very long gravitational wave that passes by, right? And that will change the flux of angular momentum. So that will make this quantity not so interesting from the observational point of view, because it cannot tell what is background and what is event. If you like a more theoretical reason, you can also say that soft dynamics is universal in a sense, and there exists an automorphism of the algebra of the U local operators that make them independent of supertranslation and boundary gravity on degrees of freedom. So you can find an automorphism that dresses observables and make them independent of supertranslation. So you can look at the dynamics of the dressed variables. Then if you want to see the effect of this supertranslation of the soft sector, you just transform back into the other algebra. So, and for instance, these are papers where we try to do this story, to tell this story in a way that is independent from the dynamics of the bulk. So, I mean, if we do that for the shear, or in particular the Bondi news for matter fields, etc., shouldn't it be possible to do the same thing for angular momentum? Shouldn't it be possible to have another object, another angular momentum that it could be as good as the first one and is independent of this of supertranslations? Well, indeed, I mean, it can, because it has been constructed. There are various choices of angular momentum existing in the literature. Here, in this talk, we will mostly work with one proposed by Chen, Wang, and Yao. And they all are variations on a theme, right? And there are small differences, but differences exist. So the definition of CWWY is to take the canonical Bondi angular momentum. Here I'm looking only at U equals plus or minus infinity. You can do the same construction at any finite retarded time, right? Well, you take these quantities and you subtract a certain bilocal, quadratic operator bilinear, really, in the mass aspect and this C, a new character that I have introduced. So first of all, let me write the subject in general for any two fields defined on Scri+. This J, if you take any field A and B, has this phase, is the integral over the celestial sphere at fixed retarded time that we will take always to be plus or minus infinity, but that's not necessary, of A times the transformation under the conformal Killing vector Y of B, and that's the same as taking the integral of the transformation of A under the conformal Killing vector Y times B. These indices, minus 1/2 and 3/2, tell us that this A transforms that A and B transform like conformal fields of weight W. So under this special conformal transformation, they transform in this way, which is the transformation law of scalars with conformal weight W. So you have to pick an A that has weight 3/2. Also, one such object is M, is the mass aspect, and another quantity, B, in this which transforms as a conformal weight of negative weight, -1/2, and that's C. What is C? Well, C is defined in terms of the shear. It's, you can call it the electric component of the shear, the electric potential for the shear. When you evaluate it at -infinity, this thing is known also as boundary graviton, and is obtained through this equation. You take the double divergence of the shear at any time. You can do this at any time. This formula is local in U, and this is equal to some square of a Laplace operator applied to C. So this equation defines C in terms of the shear. You may know that this operator actually has as a kernel the S&P waves. So if you expand in spherical harmonics this object and you take L equal to 0 and L equal to 1, actually you get 0 when you apply this operator, d times d squared plus 2. So there is an ambiguity in the definition of C. Right? You can always shift the S&P waves when you expand in spherical harmonics. Okay, so now we have all the ingredients, and well, C by construction, by this equation, transforms like a Goldstone, if I can use this abusive notation. So both C's transform with the supertranslation. M is supertranslation-invariant, so if you take these two transformations, plug them in this term, you see that the variation of this term cancels the variation of J. And you have an object that is supertranslation-invariant. In fact, at any U. And the supertranslation-invariant, what you have added is an object that is really, it's not really non-local. I mean, you integrate on a sphere, so this is inverting this operator is harmless, and it's local in U. You don't need to know what is the shear in the past, right? If you want to compute the Bondi charge at a given time, you just need to know what is the shear at the same time. Now, other definitions dress the angular momentum by using only the boundary graviton at in the far past, C minus, as an additional degree of freedom. Some of the definitions do not capture contributions to the flux that are already appearing at order G Newton square and are needed to explain radiative back reaction effects in gravitational scattering. So let me give maybe some more detail about that. Yeah? Yes. It's not. Yeah. So it's a choice. It's a choice. Yes. Mm-hmm. Mm-hmm. Well, they are. It depends. No? Indeed, they lose the dependence on the Goldstone mode. On the other hand, you know how to put back the Goldstone mode. It's a universal sector. So in a sense, you may say those are the better operators. It's you know, you have some radial coordinates and angle, and you just look at the radial coordinates, then add the angles because the angular dependence is given by kinematics in a sense. I'm actually defining another object, and this is tailored in a sense to divide what is, say, an event in the bulk or a process from any supertranslation, any ambiguity in the choice of the asymptotic frame. Because when I chose the asymptotic frame, by the very fact that there are, that you can do an asymptotic symmetry, it means that the frame is not unique. So we want to remove that non-uniqueness. Yes, I mean, this is a better behaved Goldstone, the C, because it actually lives on a compact space. So you can actually translate the C with a physical unitary. Right? While for the real Goldstone, if you try to translate it everywhere in space-time, you can't, right? It's too much energy. But this one, in a sense, is a better Goldstone. the equivalent of a Gaussian in a compact space or something. Now, as I said, there are different translation-invariant charges. So one in particular is the one that I will call JKP for my student Giovanni Nesat, Cole, and Porrati, using the universal rule of physics that you name a quantity after the last persons that discovered it. So, so this would be actually the compare Oliveri and Serraj plus physics convention that says that it was named after the last, not the first ones that discovered it. This quantity may look similar to the other, to the one defined by Chen, Wang, and Yao, but it's not, because you see that here in this JKP, you subtract the same boundary graviton, the one defined at minus infinity, both at plus and minus infinity, instead of subtracting the electric shear in the past and electric shear in the future. So there is always C minus. Both are invariant because, of course, the C plus and C minus are not really independent, so and both are transformed exactly in the same way under supertranslations. And of course, both the future and past angular momentum aspect is supertranslation invariant. At any cut, yes. Or even this, you can define it at any cut. So if you want to define it at an arbitrary cut, you substitute to m minus, say m of u, but you keep the C minus. Yes. So even this can be defined at any, and indeed that's what the original definition of compare Oliveri and Serraj was at any u. So now, if you compare these two formulas in the rest frame, what do you get? Well, you get that the change in the flux of the JKP angular momentum is the difference of these two objects, and is given by, well, the universal difference, and then this extra term, that is delta m times C minus, right? Now, since our formula is supertranslation invariant, we can use supertranslation invariance, for instance, to indeed even to cancel all the C minus, and we can also set the first two harmonics of the boundary graviton to 0 in the rest frame. And this is important, in the rest frame, not generically, because in the rest frame, this additional quantity, this bilinear, does not depend on the SNP waves of C. Okay, so now you can play around with this formula. You can use the, so in particular, in this formula, it's supertranslation invariant. You can compute this delta, this quantity in any frame you want. You'll get the same result always. So you can also compute it in a frame where all the C vanishes, and then delta JKP equal delta J canonical. Okay, delta J canonical has this form. I used the Einstein equations to transform a two-dimensional integral into a volume integral on null infinity. Yes? Oh, we'll have a lot to say about that, a lot to say later, yeah. That's actually the key of the talk. So, okay, you can manipulate this delta J and get this formula, right? And again, is we have encountered this object, is the Bondi news. So, well, I mean, again, in the supertranslation frame that C minus is equal to 0, you can integrate the Einstein equation and get an equation that gives you the double gradient of the shear, right, in terms of these quantities. Now, the flux of radiation, it's actually always order G Newton cubed, because it's, if you define it, if you look at where G Newton appears, you have 1 over G Newton times the Bondi news square. But the Bondi news for begins at order G square. The time derivative of the shear begins at order G square. It's order G cubed. This object is order G square, in part because M is defined as what we'll call G Newton times mass. And the mass itself changes when you do a gravitational scattering at order G, I mean, if there is no gravitation, there is no scattering, and m doesn't change. So this is order g square just because of its definition. So, okay, because actually this n are order of g square, and delta j equal delta j kp, we can substitute everything in this formula and discover that, well, delta j kp is order g cube. And this is bad, and to see why it's bad, we just look at the rotation, see what why this is not what we expect. Well, maybe some of you remember a calculation done in, I don't know, Landau-Lifshitz, when you have two particles in spiraling and you get delta j is order g square. So already that is a bad signal. But you can also be more general and say that the effect of radiation reaction and gravitational scattering can be computed in many ways. At lowest order in G, if you want to compute the lowest order effect of gravitational radiation, actually there is a quick way of doing the calculation. You use linear response theory. So the story works like this. You have a certain scattering angle computed in a non-radiative process, computed in a sense in a, just with two particles scattering each other off in a potential. Right? So that's chi. In a potential scattering, you conserve energy and you conserve angular momentum. When you want to see what is the effect on the scattering angle of radiation, well, you have to compute how the scattering angle changes when energy and angular momentum change due to radiation. So you just take the first derivatives, that first order, and you substitute this formula. That's linear response, right? So to first order, the effect on the angle is due to the fact that neither energy nor angular momentum are conserved in gravitational radiation. Now, delta E always begins to order g cubed, so this term cannot give any g Newton square contribution. Delta J, well, delta J can give you a radiative contribution to the scattering angle that's order g square if the angular momentum changes at order g square. Now, this delta chi is known to be order g square. There are many calculations done by various groups with different methods, starting with Bini and Damour, but now, I mean, you can use amplitudes, you can use many different methods to arrive always at the same conclusion. No matter how you compute this delta chi, this is order g square. So it means that so this delta chi begins at order, I should say, g cube, which means that delta j should begin at order g square. So the formula, the correct formulas that Bini and Damour find require that if you want to use this formula, that delta j changes at order g square, which is also, again, what you expect from perturbative calculation done in first order perturbation theory using linearized gravity around flat space, the calculation of Landau and Lifshitz. Now, so the JKP COS flux instead begins at order g cube, so you'll have to play with it. And you can cure this problem. You can add to it a supertranslation-invariant piece that gives a contribution g squared to the angular momentum. But actually, you can also do something simpler and go back to the definition given by Chen, Wang, and Yao. This definition actually is good, and it already captures the correct order G Newton square effect. Again, I remind you of the definition here. And you see that you can write this flux as the canonical flux computed in the frame, in the supertranslation frame, in which the boundary graviton, let me use this term with an abusive notation, the boundary graviton vanishes at plus infinity, minus the canonical angular momentum computed in the frame in which the boundary graviton minus infinity vanishes. So the difference, the flux of the CWWY flux is actually the canonical flux, but computed in two different frames. And indeed, this is what I'm saying here. The flux computes the final angular momentum in the supertranslation frame where the final metric is as round as possible, is the round metric up to terms order of 1 over r squared, there is no shear, right, minus the initial angular momentum in the other supertranslation frame where the initial metric is again as round as possible. So you take, if you want to compute this delta with this flux, the CWWY flux, you may say, how can you do? Well, you can use the formula, or you can say, at minus infinity, let's do a supertranslation, go to a frame where the metric is round, compute the angular momentum there, integrate n, right, with the appropriate killing vector, and then do the same thing at infinity, but in another frame. So set your detectors in the past, verify that your metric is round, then throw them away and set another set of detectors in the future. If you forget about the fact that detectors move and stay and are displaced even after a gravitational wave passes, then you'll get this flux. If you remember that, if you use always the same frame, the original round frame, right? So after a wave passes, it's no longer round, it's distorted. But if you use this distorted frame to compute the angular momentum, then you get the JKP flux. JKP flux has traded something that you would call memory effect from one place to the other. So this is also why if you just look at how you decompose this flux, you'll see that the biggest effect in the CWWY flux comes precisely from a memory effect, from the fact that the shear changes under a gravitational wave and there is a permanent displacement. So, but maybe more importantly, the frame in which the metric is as round as it can be, where it's round up to order 1 over radius square, are the frames where the Bondi charges coincide with canonical ADM charges. This is, I first saw it mentioned by Veneziano and Vilkovisky that quoted results of Ashtekar that were then unpublished and then were recently published, I think this year actually. So this may explain why this difference also coincides with scattering amplitude computations and other perturbative computations that implicitly or explicitly work in the round metric canonical frame. So in reality, when you do calculations and when you follow your textbooks, you are looking at the round frame and before and after scattering, right? And you don't keep trace of how your detectors could have moved because of gravitational waves, and that so you are effectively computing this flux. We'll come back to this point because there is a little subtlety, but let's ignore it right now. And let's come to the problem that still exists for this CWWY flux. Now, this CWWY flux is covariant if all the quantities that appear in the flux transform covariantly. So in particular, if the mass aspect transforms under Lorentz transformations as a conformal wave field of weight 3/2, and the electric shear, also known as boundary graviton, transforms as a conformal field of weight -1/2. Okay. These transformations actually follow very simply from the asymptotic form of Lorentz transformations on coordinates. So take the metric that I gave at the beginning of the talk, right, the asymptotic form. Substitute just the coordinate transformations, simply a Lorentz boost, written in terms of coordinates. But of course, you have to pass from Minkowski coordinates to U, R, and the two angles. Here, the angles are a vector of unit length instead of being θ1 and θ2, right? But same thing. Well, if you substitute what K, G are, I mean, doing just a naive computation, boom, you get that this M and C transform as conformal fields. So these are the transformations under the transformation of coordinates. These are generated by Poisson brackets of the canonical J, not the new one, not the Lorentz invariant one, and not the supertranslation-invariant one, sorry. Okay. And we'll come back to this. Yes, you have a question. Well, it's, I mean, you can say it's an explicit computation. I don't have the formula here, but, well, let me see. Maybe we can see it maybe from actually the explicit form of J. So we have to go back a little bit. When you, actually, if you can do the following. You can notice that you may start with, say, C minus equal to 0, right? And then compute the difference. So the difference of the flux of this CYY flux is delta J plus or minus infinity times, and then there is a contribution that is minus JY M plus C plus. And that's actually the term where the G square contributions are hidden. I mean, there are various ways of doing that, from, say, calculation by looking at the way in which the momenta scatter to lowest order in G, to just noticing that at lowest order, this is the term that gives the entire effect. Yes. No, you can, if you take M, really M, the mass aspect in the asymptotic metric, and just substitute the coordinates, it transforms like a spin 3/2 field. But it better transform like a spin a weight 3/2 field, because when you integrate M minus, right, you get in particular energy momentum and then some higher modes. But as we will see, it is this transformation law that ensures that the Lorentz algebra closes. So M must transform, actually, M itself, not just the flux. Well, I mean, of course, when I say that it transforms like when I talk about this, no, I mean, they do have for any M, because otherwise the Gauss formula doesn't work at all. I mean, the extra piece that they add would be non-covariant. But again, I mean, you can just substitute coordinates, right, and see how the M transform. Now, okay, let's look at the first problem with Lorentz boosts. You can take C and expand it in spherical harmonics, right? Well, you get this equation because you use just the definition of the boundary graviton, and you use the constraint equations, right? Now, and so this is simply tells us that the boundary graviton at any U, or if you want the electric shear, is determined just by the initial value. The rest, it follows from the constraint equations. Now, you may notice one thing, that here I have this expression that gives me exactly 0 for L equal to 0 and L equal to 1, right? So, and luckily this piece on the right-hand side of the equations of the constraint also vanishes for L equal to 0, L equal to 1. So for L larger than 1, you have actually, you fix your boundary graviton minus infinity, you get the shear at all U. But for L equal to 0 and L equal to 1, no. There is nothing that defines what is CLM at any value of the retarded time. So, well, CWWY, say, why not fixing them to 0, right? Just, they are redundant variables, they don't appear in the metric, they are not determined by the constraint equations, just set them to 0. Well, the problem is that you cannot do that in all Lorentz frames, because you look at the finite transformation of, for instance, a finite transformation of C, and this transformation actually mixes the components with higher L to the S and P waves. So this condition actually is incompatible with Lorentz. You start in a frame where this is true, right? But there are higher harmonics in the boundary graviton, do a boost, and then the L equal to 0 and 1 harmonics are no longer 0. So that's not, you're breaking Lorentz covariance if you if you fix this to 0 in any frame. And you can see it actually explicitly. You can really do a boost in the z direction. You have coordinates x, y, z. Then you have very explicit formulas for the objects that I defined in the previous slides. Right? You have this k minus 1, which is expressed in terms of the usual gamma and beta relativistic factors. X, y, and z are given in this way. And now you can play with it. I mean, I have this formula, I have everything explicit. Now let me take an L equal to 2 harmonic, for instance. Right? The L equal to 2 harmonic with m equal to 0 is this. Transform it. Well, we have the law for transformation of any conformal field. Boom, you get this. And now you can show that this object is not orthogonal to L equal to 0 and 1 harmonics. In particular, if you take this linear combination, the calculation is totally trivial, and you get that 3 is not equal to 1 over 3. You're done. You can also do the same thing, but by looking at the infinitesimal form of the transformations. So, too bad. We have to find another recipe. We cannot just set c equal to 0, right? In all frames. Well, let's see what it is. It's a redundant quantity, but we have to find a job for this quantity, and that's also will solve actually this problem. No, that's not the right way. Now, by the way, this problem exists for all non-definitional supertranslation-invariant charges because they all need C, and C is redundant, right? C is a redundant, seems to be redundant. So what about M? Does it create some disasters? No, if it transforms like a conformal weight field of weight 3/2, so if it transforms in this way under finite Lorentz transformations, then you can check, and it's an amusing calculation, that it does not mix higher components with lowest components. Maybe this is not the biggest surprise in this century because you can write all the harmonics of the mass aspect. And you know that the S and P waves, the L1 and 0, are actually the 4 momentum, right? Now you do a boost. Well, a boost takes a 4 momentum into 4 momentum. It doesn't take a 4 momentum into 4 momentum plus something else. The Lorentz group closes, which means, and this you can check explicitly using this formula, that when you do a Lorentz transformation, you get an upper triangular matrix, right? A matrix in which the lowest component of M always transform into themselves. But these lowest components of M may actually affect the highest mode. We transform and change the highest modes. Oh, no, this is a special conformity. Yeah. No, these are primaries only under SL2C. Yeah. So, and any W3/2 transforms like this, and luckily this means that the Lorentz algebra is a subalgebra of BMS, which we already know in a sense. Okay. Now, let's look at the second problem with Lorentz boost. I announced you two. Well, I announced the first, so there must have been something else, right? So the second problem is that actually supertranslation-invariance plus covariance means that your object is also translational invariant. So if you take an object that's covariant under Lorentz transformations and also demand that it commutes with supertranslations, then it also commutes with translations. It's unavoidable, and it follows from the Jacobi identity of BMS. Now you take F, and here I use tensor notations because they are the easiest. F is a flux, and it's an antisymmetric tensor, an antisymmetric Lorentz tensor. So now you write the Jacobi identity in which you commute flux, Lorentz generator, supertranslation S. Do Jacobi, get 0, but now by covariance, if you take an antisymmetric tensor and you do a Lorentz transformation, you get a linear combination of the same object, right? You get a linear combination of F, but F is supertranslation invariant, so S commutes with F by definition, right? It's what we want. So this term is 0, and this term is actually F, then commutes with S, then is 0, which means that actually the Jacobi identity tells that this commutator vanishes. the commutator of f with the commutator with boosted supertranslations vanishes. But unfortunately, when you boost the supertranslation, here there is a comma missing, you can get supertranslation, but also all translations you want. You can generate any translation. This, so Jacobi identity implies that actually my flux should also be invariant under translations. Everything, not just super. And so any supertranslation invariant flux in reality is an intrinsic quantity defined with respect to a particular point that defines the origin of your coordinate system. You really need to measure this flux with respect to something, and this something should be a coordinate that translates when you do a translation, right? So you really need to define an intrinsic angular momentum if you want to have an object that is supertranslation invariant. And at this point, actually, the fix of our problem is very simple. What we need is an independent covariant prescription to define this origin of the coordinates. Now, one thing that I suppose it's always in the back of our mind is that when you look at the asymptotic metric in the Bondi formulation, there is no place where to tell where is the origin of your coordinate system. When you compute angular momentum is x cross p, and you need to say where are you measuring x from, right? I mean, you need an origin. It seems that there is no place, right? But and on the other hand, there are all these redundant quantities that we introduced, this electric shear, the components with angular momentum 0 and 1, that seem to have no role. Well, I mean, could it be that actually their role is to fix the origin of coordinates, right? That's what we thought, and indeed, their role is precisely that. These C's are not so redundant. They can be used to fix a preferred origin for the system of coordinates. So let's see how to fix that. And let's start first in the initial center of mass rest frame. So let's look at the rest frame where your system has no momentum, right? It sits at rest. And this means that there is no L equal to 1 harmonic in the mass aspect, right? So let's go to this frame. This frame, of course, allows for translations, right? You can still translate the origin of coordinates. And to fix this origin of coordinates, we do something very simple. We require that the new angular momentum, the CWWY, actually the generators of the Lorentz transformations vanish when the killing vector y describes a pure boost. So you have one frame, right? You have fixed the frame. Now it's unambiguous what is rotations and what is boosts. Boosts in the language of conformal killing vectors, by the way, are gradients of an S-wave scalar to base this equation. So that's the request. Take these three vectors, the three pure boosts, in the center of mass and require that the boost charge vanishes. Okay. This is a very explicit formula. Indeed, you can see how explicit by just expanding C minus in harmonics. By the way, I'm doing first I'm fixing the initial frame, the frame before gravitational radiation has arrived at u equal minus infinity. Then I'll have to do the same thing in the future, right? Well, let's start first with the past. Now, if you take this expression and expand it in spherical harmonics, you'll actually get, after some rather straightforward calculations that use the fact that y is a conformal killing vector, that's a pure boost, that's a gradient of an L equal to 1 harmonic, well, you get that actually the three L equal to 1 components of the boundary graviton are fixed by this very, very explicit formula in terms of all the other components, in terms of the canonical angular momentum at minus infinity and this bilinear. But in this bilinear, here you have only the additional higher harmonics, L larger than 1, right? So this is as explicit as it gets. This formula doesn't tell me anything about the scalar component of C, but this never appears in the rest frame formulas for the angular momentum. In the angular momentum formulas, well, the only term that, and even for the boosts, right, this C is either derived, either you take a gradient and then you get nothing, or it's multiplied by the momentum which vanishes in the rest frame. So this we can set to 0 happily. Now in tensor notations, what we have done, right, is that we took in one particular frame, we took the 0 I being a space index, components of the Lorentz charges, and we set them to 0. Right? So if you write, so this is what we did. So far we worked in the rest frame, but now if we rewrite what we did in what we wrote in terms of killing vectors in terms of vector indices, I mean, then it's obvious how to generalize to any frame. Right, what we have just done. You want the equivalent of this condition in an arbitrary frame. Well, clearly you have to impose that the J mu nu contracted with the energy momentum vector vanishes. Right? And that's, this energy momentum vector is something that you compute in terms of the angular momentum aspect in any frame. You can compute it. You can compute J and do this, and that will define your frame everywhere. And this thing is covariant on the nose, right? Okay, so if you like to stick to these notations, then you may say, oh, how can I rewrite this condition in terms of conformal killing vectors, mass aspect, etc. So, as they said of Fellini, why to use 2 words when you can express the same idea with 8, right? So let's do this. You can think of these formulas as formulas that associate real numbers to the vector y, right? So because I mean these are real numbers, right? For any choice of y, for fixed m and c minus. So this you can think of this as and the map by construction is linear in y. So this is actually an element of the dual vector space of the conformal killing vectors. So take the dual, you are back. So take what I call star of j. You are back into the space of conformal killing vectors, and then you can. This condition becomes simply that the mass aspect, the variation of the mass aspect with this conformal killing vector with star j is equal to 0 for L equal to 0 and 1. So that's the covariant equation that I wrote here, but written in terms of these quantities of j's, y, etc. Right? You can be very explicit if you go to a basis, right, of both the original space and the dual space. Okay, so I'm almost at the end, and I think that I'm doing well with time. Now, let me just notice one thing. This condition, the condition that the boost charge vanishes in the rest frame, is actually implicitly used in most papers on gravitational radiation, because when they have to choose a frame, they choose a center of mass rest frame in which the origin of coordinates is the center of mass. It goes without saying, but if you look at, for instance, Manohar and collaborators, etc., this choice is always implicit, because it's what you will do even in a basic physics course. Right? If you want to do a scattering process, go to the center of mass. So this actually is a very natural choice. It's much natural than setting these redundant components of the boundary graviton to 0 in one frame chosen at random, even if this frame is the center of mass. Because this is really what you will do in practical calculations. Yes, you have a question. Well, this is actually the next thing, right? Because to completely fix the flux, right? To give a definition that's covariant and supertranslation-invariant and translation-invariant, for the flux, we also have to define what are the redundant components at plus infinity, right? I mean, if we want the flux at any finite time, we'll have to do it at any time. And here you have several choices, right? You can choose that the C plus is equal to C minus, so you can say, well, we have fixed this. There is nothing that tells us as C evolves, so let's give this choice that the S&P waves of C are exactly the same in the past or in the future. Or you can say, no, that's not a good idea. We can also impose that the boosts vanish in the final rest frame. In this definition, you are computing angular momentum flux by keeping the Lorentz frame the same, and also the origin of coordinates the same. In the second one, well, this is actually, you're computing an angular momentum in a given Lorentz frame in the past, but then you're computing the final angular momentum in another frame. Because, well, when you start to go higher in an expansion in G Newton, right, the radiation can change the rest frame. So you can start with an object that's at rest. This object may radiate and start moving like a rocket. Right? So these are actually, they will give two physically different fluxes. But you understand exactly where is the difference. Right? The difference is whether you keep the same Lorentz frame or another. The same Lorentz frame with the same origin of coordinates with the same center of mass versus two different Lorentz frames before and after scattering. So you have your choice. Now, it's easy to show that actually to order G square, the two prescriptions agree, and the difference starts to appear to order G Newton cube. So at least at lowest order, there is. Yes? Mm-hmm. You can. We didn't do that. Maybe this is in the to-do list. There are a few complications. A few complications, of course, is that if you are at finite U, you also have the freedom to choose different cuts of U, because you can do a super translation that changes the local equal time surface. And also the transformation laws of all the fields involved become significantly more complicated. So yeah, this was a clean thing. And then if you want to go at finite U, you have to think about additional ambiguities that are perfectly physical and you can introduce. I mean, how you synchronize your clocks at finite time. For the one last thing that I want to mention here, you may have to look at finite time fluxes at some point, but let's postpone this moment as much as possible. So, okay, after both future and past electric shears are fixed by whatever prescription you like, the covariant flux is given by this expression when both J plus and J minus are computed in the round metric. That's the main point. You take round metric in the past and round metric in the future. And as I mentioned earlier, right, it was recently argued that when you compute the canonical Bondi angular momentum in the round frame, you are computing actually the ADM angular momentum using results of Hachtecker et al. So this delta J is the change in the total ADM angular momentum. And actually for some simple scattering systems with say two particles and equal mass, different mass, Riva, Vernitz, and Wong verified that in fact this difference coincides with the formulas of Bini, Damour, Manohar, and many others. Now, this identification, the identification of the Bondi charge with the ADM charge, is valid only for the ADM Lorentz generators defined with some special restricted asymptotic boundary conditions that forbid supertranslations. If there are supertranslations, there is no angular momentum. There are, as we have just seen throughout this hour, there are many. So this identification also worked better when we were less able to change boundary conditions at space infinity. Because if you relax, now we know how to relax space conditions, asymptotic conditions at space infinity, and get actually the entire BMS group. In this case, there is no unique definition of angular momentum, and you're back to the same problem. So appealing as it may be, this identification, it's only valid if the boundary conditions at space infinity are artificially restricted to forbid supertranslations, because by now we know how to do better, right? So, okay, that was a word of caution. But maybe I have actually to tell you something else, and I think that by the standards of this workshop, I have practically an hour, and they take much less. So, if you look at compare Oliveri and Serraj, and also us, right? We show, I mean, all this group show that if you take the generator of Lorentz transformations, the true generator, the one computed at infinite past retarded time, J minus, right? So if you compute this object, and notice that here, all the definitions of the charge at minus infinity coincide, whether you use CWWY, JKP, etc. They are all give the same result. But in these definitions, what we did and what everybody did was simply to consider only the higher harmonics of the boundary graviton. So here you insert only the higher harmonics, you set to 0 the harmonics, L equal to 0 and L equal to 1. Right? So, well, you take this object, and then this generates a Poincare algebra. So how is it consistent with what we said before? Where we say, no, actually, this doesn't generate the Poincare algebra, you mix higher components with lowest. Well, the point is that this particular combination does not generate the Lorentz transformations induced on the asymptotic metric by the coordinate change. So if you do a coordinate change, you get a certain formula. You get that the fields, what we call C and M, transform as conformal vectors under SL2C. If you take this generator, you generate a linear combination of Lorentz transformations plus generalized supertranslations that cancel the action of the Lorentz transformations on the higher harmonics of the mass aspect and the boundary graviton. I say generalized supertranslations because you have to include the boundary graviton as one of the generators of your algebra. So if you take an algebra that's BMS plus the boundary graviton, right, then you have all that is, this object is defined in the algebra, well, in the enveloping algebra, and then it really fits the bill because, and this is more or less obvious, right? If you take this object, this was constructed to be independent of the boundary graviton and supertranslation-invariant. But so if you compute the Poisson brackets, or the commutators, if you prefer, of, say, the boundary graviton, higher harmonics of, and this object, well, since I is independent of C, you get 0. On the other hand, the same Poisson brackets can be read in the opposite way, as the action of C, of I on C. You can think of this as C generating a transformation of I, or of course I generating a transformation of C. If you take this second point of view, this tells you how the boundary graviton transforms under a Lorentz transformation. And by construction, this is 0. Same thing for the mass aspect. So by definition, this I generates a mix, right, of Lorentz boosts or rotations and super translations, generalized super translations that removes all that does not act at all on the higher harmonics of the mass aspect and the boundary graviton. Right? In fact, if you just stare at this object belongs to the universal enveloping algebra of generalized BMS. It is not even an element of BMS algebra because this term is quadratic in the generators. Okay, so that's all. Let's conclude with a summary. The formula that we obtain may be interpreted as the difference of ADM angular momentum before and after a burst of radiation through non-infinity. Why the formula works at all, what is special about the canonical frame, or in fact the standard ADM angular momentum. I mean, in some sense we may say, yes, the formula works because when the calculations done perturbatively compute the ADM angular momentum, but again, now we know that there is no such thing as the ADM angular momentum because we can have super translations also at space-like infinity. So we have to, again, to find a way to pick up a particular value of ADM. But at least we know why, when you choose the standard boundary conditions at space-like infinity, right, and you get what we have been calling ADM angular momentum for many years, you get the results of perturbative calculations, and B, you get something that coincides with the this modified CWWY flux. Now, one question is whether we can make sense of other formulas. For instance, identifying this delta J. Here I should have put JKP or maybe COS. So can we also make sense of formulas that begin at order G cube, G Newton cube? Right? Could we essentially set up an experiment where you have asymptotic detectors that just see the G cube part of the flux and not the G square part? But we have an idea, right? I mean, some of the things that I said earlier may actually solve this problem. Would be interesting to find a link with the ADM quantities computed at space like infinity when asymptotic fall-off of the metric is relaxed to allow for the full BMS algebra. So it would be nice to have a matching, not only of the algebra generators, but really seeing how the generators defined at null infinity go into the generators defined at space like infinity. Also, maybe practically, and the most important question is, can we also define infrared safe fluxes? Because so far the definition that we gave only removes the effect of really supertranslation, which is radiation with wavelength exactly equal to infinity. So how can we remove the effect of finite wavelength radiation? We would like to have quantities that don't depend on any gravitational wave with wavelength much bigger than, say, the typical size of my system of binaries, right? I mean, we want to be able to remove some soft but finite wavelength background from our definition. To do that, it will be necessary to define, I think, fluxes computed at finite retarded time, and then be more careful about all the additional definitions and ambiguities that you encounter when you work at finite U instead of just infinite U. So this is the time to stop. Thank you very much.